Well, let's look at a couple of terms. One of them I'm sure you've heard of, and the other one maybe not. Well, this definition, this is the real number set, right? This fancy R, and then in brackets you put X. What this represents is the set of all polynomials that have this type of number for the coefficients, real numbers. So it's the set of all P such that P is a polynomial in the variable X having real coefficients. So 3x squared plus 2.5x plus pi is in this set. And we know this one from pre-calculus or algebra. X in the real numbers is a root of f of x if f of x is equal to 0. That's just the definition of a root. Now let's look at a relation. Relation takes these ordered pairs, a polynomial and another polynomial, such that f and g of x have a common root. So R contains every pair of polynomials with real coefficients such that they have a common root. That is a relation on this set here. So, for example, if f of x, these are the factored forms of three quadratic functions. F of x is x minus 1 times x minus 2. G of x is x minus 3 times x minus 2. H of x is x minus 1 times x minus 8, which are related. Well, let's see. F and g are related. So I could say something like that ordered pair is in that relation because f and g have a common root. 2 is a root of this one, 2 is a root of that one. What else? F and H. Is another element. So we could say F is related to G and F is related to H. Now is G, the other option is GH, and it is not. They do not share a common root, so I'll say GH is not an element of the relation. Okay, now a little bit more terminology and a few examples. Let this symbol be a relation. It's the squiggly, it's the, what do you call it, the tilde maybe? It's just a squiggle. And it's frequently used to mean a relation, a generic relation. You can define it whatever you want it to be, whatever operation. Let this be a relation on some set A. And just to make it more succinct or concise, we frequently write this, where A is a set, and that's a relation on the set A. So each ordered pair, each one of them would come from the set A, and they would be in the relation if A is related to B, if A and B are the two elements in A. You can use any symbol. Okay, for C and D in the set A, what does that mean? It means that C is related to D. So there are three terms we want to define, and you've probably heard of all of these. This relation is blank if A is related to A for all A in the big A. That is symmetric. I'm sorry, reflexive. Think of it being reflexive, reflective like a mirror. A is related to itself. Okay, the next one. What it would be called if A relates to B implies that B relates to A. It's almost like commutative, but we'll call it symmetric. And the third one, let's see what it says. If A relates to B and B relates to C, implies A relates to C, right here. That's the transitive property. And it has to hold true, I've been mentioning this, for all the variables in the set A, for all A, B, and C in A. Last one is transitive. Okay, we got a lot of examples we'll look at. Just a couple more in this, 3 I guess, in this video. We can use, and you can do this on homework, if I ask, is this reflexive? Is it symmetric? Is it transitive? You can just use capital R, capital S, capital T. Reflexive, symmetric, transitive. So A is the set with only 3 elements in it, A, B, C, where this relation is defined to be this set of ordered pairs. A, B, A, C, B, A, B, 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 C, C, B, C, C. Notice that one of the possible ordered pairs is missing. So maybe that's going to help us decide. Okay, is it reflexive? Is each one of these 3 letters, does it relate to itself? And the question is, let's see, the answer would be, let's see, here's AA, so we know A relates to itself. So does B, and so does C. So it's absolutely reflexive. So I'm just going to put an R there. Now, I know what I'll do. I'm going to do R, S, T, and I'll cross out the ones that are false. R is good. We leave the R. How about symmetric? For example, here is AB. Does that imply we have a BA? Yes, it does. AC? Is there a CA? No, there's not. I picked the one that was going to cause the problem. BA has AB. Well, BB has BB. AA has AA. CB has BC. Which one did I say was the problem? AC does not have a CA, so it is not symmetric. Is it transitive? Well, if it had every one of the possible elements, it would be transitive. But I don't think it is transitive. Which one is missing? CA is missing. Well, notice that CB is there. And notice that CB, BA is there. I'm putting a question mark above that. Does that imply C relates to B, B relates to A? Does C relate to A? No, it doesn't. It's not in there. So I'm going to put CA here, just is not. So no, that's not there, so it is not transitive. I think that's the only possible counterexample to show that it's not transitive. Okay, next one. Very simple to define. The set is all real numbers and equals. Well, do I even have to write anything down for this one? Is it reflexive? If you take any real number, pi, is pi equal to pi? Of course it is. Is 10 equal to 10? Of course it is. That's obviously going to be true. It is reflexive. Is it symmetric? If, for example, I'll give one example, it's really going to be simple. If A is equal to B, is B equal to A? Of course it is, and it actually means it would be the same number. So 5 is equal to 5 means if you switch them around, 5 is also equal to 5. So that's symmetric. Transitivity, is it transitive? Of course. If A is equal to B and B is equal to C, doesn't that mean A is equal to C? Of course it does, so that's everything. Okay, how about this? Is this relation reflexive, symmetric, and or transitive? Reflexive. Well, I like to pick an example just to kind of get the feel for it in my brain. 1 is not equal to 2. If 1 is not equal to 2, does that imply that 2 is not equal to 1? It certainly does. Doesn't matter which side, you can switch the left and right and it will hold true. So it is reflexive. Let's see. Nope, that was symmetric. I went out of order. Reflexive is 2 not equal to 2? That's false. So I'm going to put the R there and say no, it absolutely isn't. Pick any real number and say it is not equal to itself. That's a false statement. So any number would be a good counterexample. And the last, we did symmetric, and then transitive. Well, if you were to do an example like this, 1 is not equal to 2 is not equal to 3. Does that mean 1 is not equal to 3? Well, by chance it does. It is not transitive. And an example would be 1 is not equal to 2, 2 is not equal to 1, but 1 is equal to 1. A better way for me to write that would have been to say 1 is not equal to 2, and 2 is not equal to 1, but 1 is equal to 1. So it is not transitive. That one is only symmetric of the 3.